All right. So let's kind of jump right in here. Read through it. The penguin population on an island is modeled by a differentiable function p of time t, where p of t is the number of penguins and t is measured in years for 0 less than or equal to t less than or equal to 40. There are 100,000 penguins on the island at time t equals 0. Important piece of information right there, right? We have an initial quantity. The birth rate for the penguins on the island is modeled by this. B of t equals 1,000 e to the 0.06 t penguins per year. And the death rate for the penguins on the island. No one wants to think about dying penguins, right? But, well, there it is. All right. So 250 e to the 0.1 t penguins per year. All right. So letter A, what is the rate of change of the penguin population on the island at time t equals 0? Okay. So what things are affecting the rate of change of the penguin population? The birth rate, the death rate. Okay. And so how would we represent then the rate of change of the actual population that's on the island at a particular time? B of t, birth, minus death. Exactly right. So birth rate minus death rate. Okay, but we want to evaluate that at what specific time? 0. So B of 0 minus D of 0. Okay. This one we can do mentally, right? I mean, of course, you know, use your calculators whenever you want in this particular problem, but this one we can do mentally, right? We can put the 0 in for t here. 0.06 times 0 is 0. E to the 0 is 1. So times 1,000 there gives you 1,000, right? D of 0, again, it's going to be, well, it's going to be e to the 0, which is 1, times 250, so minus 250. Okay, and so we get, yeah, 750 penguins per year. Okay. So with that kind of, you know, with that kind of number, you might think, oh my goodness, the penguin population, you know, as time goes on, is going to explode on that island. But of course, you got to remember that as time goes on, the birth rate and death rate are also adjusting simultaneously too. So we might, you know, that's at time 0. Okay, at time 0, at that instant, the penguin birth rate or penguin population rate is that on the island. Okay, but that's the answer right there. Okay, letter B. Okay, to the nearest whole number. Okay, so we are going to be rounding here to the nearest whole number. What is the penguin population on the island at time t equals 40? Okay. So we want to know the actual population. So here we have a representation of the rate of change of the population on the island. So how can we come up with the actual quantity for the population here? What should we do with this? Okay, so right, we're going to start with the 100,000. Right, Bryce, exactly right, because there's already 100,000 penguins on the island. And we're going to add to that, what? You going to continue, Bryce? Okay, so, and what's the integral, what are our limits of integration going to be? From what to what? 0 to 40, you got it, of B of t, the birth rate, minus D of t, the death rate. Yeah, dt. Okay, there's our setup. Starting with 100,000 penguins, we're going to add to it, this is the net change, right? The net change in the population. Okay, so we're starting at time t equals 0. We're going to iterate from 0 to 40, add, you know, whatever this net change is. Could be positive, could be negative, and to that 100,000. And so we'll see where we end up. Okay. So again, this would be a good opportunity here for you to make sure you can type things in your calculator accurately. I put the, you know, birth rate in Y1, the death rate in Y2. Okay. So even those of you that don't have the pretty type on the calculator, you know, those of you that have like the older calculators or whatever, I would still recommend putting things in Y1 and Y2. I think it just helps with the organization. In fact, even more so for you guys maybe to have it like that, just because it's helpful with the, you know, the writing everything out and all that stuff. Okay. Oh. see, you get 133,058 there. Okay. Oh, question. More.
In like the old calculators, it's like y1 minus y2, comma, and then the A or the B first.
Let me show you here. Oh, it's I think it's A comma B.
Okay.
Yeah. It's A then B. Yeah, it should be. Let me check here though. I can do that. Yeah, there it is. In the Yes. Good. I'm glad that you're practicing this, right? Because it is important to get all those different commands down. When you're using fn int, it is, the integrand goes here. Okay, comma, x always is going to go there. We're not going to put anything else there ever. Okay, and then a, and then your b goes there. Okay, so this is equal to the integral from a to b of the integrand dx. That was an integrard. Okay. All right. Any questions on? We're good. We're good so far. So far, so good. Yes. All right. Letter C. Again, to the nearest whole number. What is the average rate of change of the penguin population on the island for 0 less than or equal to t less than or equal to 40? Okay. So, average rate of change of the penguin population on the island for 0 less than or equal to t less than or equal to 40. So, is this the f of b, or population of b minus population a over b minus a, or is this the 1 over b minus a times the integral thing? What should we do here? It's going to be the first one. Okay, it's going to be the first one we're going to use. We're going to use average rate of change. We know what the rate of change is. Okay, well, sorry, not the rate of change. Sorry, we have the average rate of change of the population. So it's the population is our function there. Okay, p of t. And so the work here, we're going to say like p of 40 minus p of 0 over 40 minus 0. Okay, p of 40 minus p of 0 over 40 minus 0 for the average rate of change there. The good news is we have all of this information already. Right? There's no extra work to be done here, really. What is p of 40? What we just got. Yeah, exactly right. 133,058. What's p of 0? Yeah, remember, p of 0 is the population at 0. P prime, the rate of change of the population, is 750. Does that make sense? So it should be 100,000 over then the 40 there. Okay, which equals then 33,058 over 40. Okay, you can leave it like that. I'm going to put it in penguins per year. Okay, like that. And you can leave it like that. I guess it says to round to the nearest whole number, which I guess means they want us to actually just come up with a decimal there. So I guess we could say 820. Ooh. The 5 would round up. I don't know. I guess I'll say 827 there. Okay. Okay.
Yeah, you're missing 5,000. You're missing something.
I'm missing something?
Yeah.
What am I missing? Sorry, I don't understand.
No, never mind.
You got 826? So right, so like so I saw like the hundreds place. I thought, okay, it's a 5, so it would round up to a 0.5, and then the 0.5 would round up to 827. So you see what I'm saying? That's all. I don't know. Yeah. So, but again, I think it's okay to stop right here too. You don't need to, get the actual decimal, and you can just stop right there. Not to worry about the rounding and stuff too. One thing I do want to say though, Sean, you weren't wrong. We could use the other formula here, the average value formula, okay? But if we're trying to find the average rate of change, that means we would apply the average value formula to the rate of change of the population. So in other words, the alternative here would be 1 over b minus a, integral from a to b, of the rate of change of the population. And again, what represents the rate of change of the population? B of t minus d of t. So you could I should do 0 to 40 here, not that. Okay, so, or you could do that, and you get you the same answer there. All right, so you weren't wrong. Both would work here, okay? Both would work here. All right. So, letter D. Letter D. To the nearest whole number. Again, whole number, okay? Find the absolute minimum penguin population and the absolute maximum penguin population on the island for 0 less than or equal to t less than or equal to 40. Show the analysis that leads to your answers. All right. So, we need to come up with what points as our possible candidates for the absolute minimum and absolute maximum. Critical values and also the endpoints of our interval, right? We already have the endpoints of our interval, so we can already go ahead and say the population at 0 is 100,000. Okay, we can say the population at 40 is 133,058. Okay. All right. But then we need to come up with our critical numbers. Critical numbers occur when what is true? Derivative of 0 or undefined, right? Okay. So what represents the derivative of this population, or the rate of change of the population? What thing does that represent? Or what thing represents that, I should say? B of t, birth rate minus death rate, right? Okay. So we want to say b of t minus d of t, and see when it equals 0. Okay. Or you can think, when does b of t equal d of t? Okay, either one of those will get you the correct t values. Okay, so let's go ahead and figure that out here on our calculators. I'm going to go ahead and just graph these two functions simultaneously and see if I can find the points of intersection. I'll just try it that way this time. Okay, and again, I want to make sure I'm on the interval from 0 to 40 too. So 0 to 40, I'm probably going to have to adjust my calculations here. So let's say I go up to like 100,000. All right, go from there. Okay, way too high for the y value there. Let me try 50,000. Still a little higher than I would like. So let me go down to like 30,000. So it looks like it crosses just once, right? I'm going to adjust my window just a little bit more. Okay, yeah, looks like it crosses just at one point. So second trace, intersect. And yeah, at about 34.657. Okay, 657 years there. And of course, if you did the alternative way, so again, I was looking to see when b of t equals d of t, but you could do it this way too, where you do the y1 minus y2. Okay, and then locate the zeros for that. Okay, and so there's our 0, and you can't see it. There it is right there. Okay, so you can also do it that way and find the 0 command. Let's see. And we get that 34.657 again, doing it that way too. Okay, so either subtract the two, see when it equals 0, or set them, equal and see where they intersect. Okay, that point. Okay, and then of course we plug that in. Now we want to evaluate our population. We want to evaluate the population at 34.657. Okay. So what kind of calculation are we going to do to evaluate the population at this time? Well, what's our starting population? 100,000. We're going to add to that the net change from, that's the population at time 0, and we're going to add to that the net change up to 34.657. And again, it's going to be B of t minus D of t dt. Okay? And so we can just do 100, 1, 2, 3, plus math 9, and oh, I'm going to go back to my pretty type. Sorry. Okay, and you get 139,166.666. Okay, so we'll say 0.667, I guess. Or I guess maybe we're supposed to round this one and say, yeah, to the nearest whole number, so we'll round that. So 139,167 penguins. Okay, so what is the absolute minimum penguin population? It's at t equals 0, but it's asking for the population, so here's the absolute minimum right here. The actual population is going to be the answer here. 100,000. Okay, and then where's the absolute maximum? At that critical point. There it is. All right. That one wasn't too crazy. Very similar to previous ones we've done. Nothing like too weird with twists or turns or anything like that. So pretty straightforward. And that's a Form B kind of question, I think, too. So kind of interesting there. All right. I believe I have. Let me see here. Nope. Okay, never mind. Okay. Thought I might have. Okay. Questions on any of that? All right, let's continue on here. Okay. So, now we've got particle motion. Okay. So we want to use this to help us out here. All right, it's been a little while since we talked about particle motion. This is looking... Well, actually, no, I don't think it's going to be a non... I think this will be calculator active still. Okay. So, for example 25 here, we've got a particle is moving along a line, okay, such that its velocity can be modeled by v of t equals 4t cubed plus 6t squared minus 7e to the t. Okay? Alrighty. So, the first thing we want to do here is to find the position of the particle at time t equals 3, given the particle is at s of 0 equals 13. All right, so we want to find the position. How do we find the position given the velocity? What should we do? Integrate, right. Okay, so we're going to integrate the velocity here. So integral, and, well, how should we go about integrating the velocity here? What should we do? Do we need to use a definite integral here, or do we need to use an indefinite integral? So in other words, should we use limits of integration, or should we not use limits of integration? Sean, you have an idea? You have the integral from what to what kind of thing, like to like. Okay, so, all right, so you just want to integrate this indefinitely. So we'll say integral of 4t cubed plus 6t squared minus 7e to the t dt. We'll integrate this, okay, so we end up with t to the 4th, right, because it's going to be, well, I guess I'll do this. 4t to the 4th over 4 plus 6t cubed over 3, and then the integral of 7e to the t is 7e to the t, and then I also need a plus c. Okay, so that is my position function. But how can I figure out what the c is? Put 0 in for the position instead of equal to 13. So we'll say 13 equals, and I'll simplify this here. So we have 13 equals 0 to the 4th plus 2, 0 to the 3rd minus 7e to the 0 plus c. Okay, so c is going to be 13. No, yeah, e to the 0 here is 1, so this is a minus 7, right? That's 0, but that's minus 7 plus c, so we're going to have to add 7 over, so it ends up c is 20. And so then s of t equals, t to the 4th plus 2t cubed minus 7e to the t plus 20. And so that's our final answer. No. Okay, what are we supposed to do now? Plug in 3, right? The ultimate question here, find the position of the particle at time t equals 3. So s of 3 equals then 3 to the 4th plus 2, 3 cubed minus 7e to the 3 plus 20. Okay, you can leave it like that, right, because it's just arithmetic. Yeah, bless you. Oh. I'll get the decimal here for you in just a sec. And the decimal is about 14.401. Okay, just like that. All right. We also could have used a definite integral here. So, the problem does not ask us to find the position and then give the position of the particle at time t equals 3. It just says find the position of the particle at time t equals 3. Okay? So what could we have done here? Well, what do we know? We know that the particle is at 13, position 13 when the time is 0. So we could have started here with a 13. That's when t is 0. And then add to that the integral, and we would integrate from what to what? 0 to 3 of the velocity function. Okay? This would also yield 14.401. If you don't believe me here, I'll just type it in real quick. Can I do it there? So 13 plus math 9, the integral from 0 to 3 of 4x nu 4x to the 3rd plus 6x squared minus 7e to the x. And there it is also. Okay? There it is as well. Okay? Starting from that known position, right, at time 0, we can then integrate from 0 to whatever other time of the velocity. That will give us the new position. Okay, so that's an alternative way to do it. So we could also say then s of 3 equals that as well. Okay. So that's two alternative ways to do it there. Also gives you 14.401. Okay. Letter B. Find the total distance traveled by the particle over the first 3 seconds. Total distance traveled over the first 3 seconds. Okay. This is where, I don't remember where we talked about this. Kind of scratching my head a little bit, but it's a thing, okay? So total distance traveled is different from net displacement, okay? So let's answer letter C first, and then we'll talk about what the total distance traveled is, okay? So let's answer letter C first. Find the displacement of the particle over the first 3 seconds. What does that mean we're supposed to do?
13 plus.
Or maybe instead of displacement, what if I want to say net change there? This is the same idea as net change of the position of the particle over the first few seconds. Yes, we're going to integrate from what to what? And what are we integrating? Not s, just the velocity. Just the velocity, yeah. That's all it is. Okay. This will give us the net change in position. Okay. The net change in position. All right. And so that's something we can do on our calculators here. Don't need to worry about. I mean, I guess we could use, you know, the thing we found, but I think we're going to use our calculators for this. So 0 to 3 of 4x to the third plus 6x squared minus 7e to the x dx. Okay, so 1.401. Okay, and I guess this is, we don't have any units, so never mind. We have seconds, but we don't have a unit of position. Okay? Okay. So displacement, that is like how far away is the particle from where it started at time 0 to where it ended at time 3. Okay? That is net displacement or net change. All right? So, for example, if like I were a particle, what I mean, like the difference here between net displacement and total distance traveled, right? If I were a particle and I moved like time 0, I was here, okay? And then over time, I moved left a step and then back right to where I started, okay? And that's like where my time ended. Let's say if that's time, 2 seconds there or something like that. So time 0 seconds, I was here, and then I do this and back here, and that's at time t equals 2. What is my net displacement there? 0, right? I have not changed from where I started to where I stopped. My net displacement is 0. But what would my total distance traveled be? It would be the positive 1 motion in this direction, the negative 1 motion in this direction, but it's going to become a positive 1 because we're talking about the total distance I've traveled. So it's a 1 plus 1, so that's 2. Okay? So the distance that I've traveled, the total distance I've traveled is 2. The net displacement is 0 there. Okay? So to find total distance traveled, it is the integral of the absolute value of the velocity from 0 to 3. Okay? Net displacement, when you integrate from 0 to 3, the velocity could be positive, could be negative, and that results then in sometimes, those things kind of canceling out. When you integrate from 0 to 3 the absolute value of the velocity, you eliminate those negative regions of the graph, okay? Where the graph could be above the x-axis or below the x-axis, you make it then just all positive, and so it gives you the total distance the particle has traveled, okay? This is only going to tell you, overall, what's the total change from where the particle starts to where the particle stops. This tells you how far the particle has traveled in the meantime, okay, between, how far the particle actually has traveled from 0 to 3. Okay, this is something that requires, then, of course, a calculator. Okay, so Math 9, 0 to 3, and then, of course, Math Num ABS, right, and then we'll type in our function there, 4x to the third, 6x squared minus 7e to the x dx. Okay, and we end up with 27.783, we'll say. Okay. Question?
If you're like stepping thing, the distance traveled is 0, but the 0 steps, and then the displacement is 2 steps, or is it switched?
Okay, right, exactly. So when I do the steppy thing, if I go like this and right back to where I started, my net displacement is 0 because from where I started to where I finished, I have not, my final position change, my final change in position is nothing. I've gone right back to where I started. But because I did do some motion here, I went left 1 and right 1, right? That's kind of like the net displacement showing how it kind of cancels out. When going left 1 is a negative, and then adding 1 back to the right is a positive, so they kind of cancel out. That's net displacement. Okay. Total distance traveled, though, I actually went 1 unit out and then 1 unit back, so it's a total of 2 units. So that's total distance traveled. Okay, and that's why we do the absolute value there to kind of cancel out those negative regions, make them positive and stuff. Okay, so all right. Next, letter D wants us to find the average acceleration from the time interval 3, 5. Okay. So what's one way we could do this? There's two at least, right? Two ways here, I could say. Okay, so 1 over b minus a. So we could use average value. Okay, we could use average value. If we're going to use average value, what function do we need for the acceleration? Okay, how do we find, do we have the acceleration? How can we find the acceleration? Derivative of velocity. Right, so so we'll say a of t, I'm just going to go ahead and take the derivative of it, is going to be what? 12t squared plus 12t minus 7e to the t. Okay, and so if we're trying to find average acceleration, right, it's not saying average rate of change, it's saying average acceleration. So we could use average value of the acceleration, which will be, as Lander said, 1 over b minus a, 5 minus 3, integral from 3 to 5 of a of t, dt. Alternatively, we do know acceleration is a rate of change of something. It is the rate of change of what? Velocity. So alternatively, we could talk about acceleration as the rate of change of the velocity and be asked, what is the average rate of change of velocity? In which case, we would use what formula? What's the average rate of change formula? F of b minus f of a over b minus a. Or in this case, since it's the average rate of change of velocity, it would be v of 5 minus v of 3 over 5 minus 3. Can't you kind of see, though, that these two things are going to be the same? What is the integral of acceleration? Conceptually, it's the velocity. We're going to evaluate the velocity from 5 to 3 and then divide it by 5 minus 3. I mean, it's the exact same thing. You can see it right here, okay, happening. It's the exact same thing we're finding in both scenarios, just two different ways about going about doing it. Okay? So I'll go ahead and just do this all at once. Please be careful when you type this in your calculator. Please don't forget that 1/2 out front. Okay? Please do not forget that. Very easy to do. Okay, so acceleration we said was 12. So I get negative 205.147. Okay, again, there's no time, so we'll just have to kind of do it that way. There's no, or sorry, no distance units, so we'll just have to leave it with that. Okay, or I guess you could say units per second squared, but anyway. And then v of 5 minus v of 3, so I'll go ahead and do that too. Let me just plug the velocity in here. I should have done that like probably a million years ago, but 4x squared cubed. 4x cubed plus 6x squared minus 7e to the x. And then, let's see here. y1 of 5 minus y1 of 3 divided by 2. And there it is as well. So that one works as well, as we expect it to. So either way there. Yes, Lily.
Is it only speed that you use the absolute value of it?
Speed is the absolute value of velocity, yes. Yes, but yeah, so
I'm just wondering, like, if there's 10 times you don't include it?
when you don't include what?
Like the negative.
Oh, the negative, I see what you're saying. Yeah, so yes, only when we're talking about like a speed, you would never have a negative speed. You never have a negative speed because of the absolute value kind of stuff. Okay, yeah. I mean, in a sense, you can also say total distance traveled, it's the integral of the speed of the particle too, right? Because isn't the absolute value velocity speed? So you can think of it that way too. But so that would also never be negative. The total distance traveled would never be negative because again, a total distance wouldn't make sense to be negative. All right, last thing here, letter E, find the average velocity. Okay, so again, two ways to go about doing this. Option 1, we could use the average value of what? Average value applied to what function? The velocity, because we're asked to find the average velocity. So we could say average value of velocity, which would be 1 over 5 minus 3 integral from 3 to 5 of v of t dt. Okay. Alternatively, we could use the average rate of change formula, but we would need to apply that to what function? Position. So we could also say average rate of change of position. Okay, which would be then, I guess we used s for position, yeah. S of 5 minus s of 3 over 5 minus 3. Okay. Here, strategically, I think this is the better way to go, right? We already have the velocity. In your earlier work, you maybe did not calculate what the position was, right? Maybe you did this for letter A instead of finding the actual position here. So it's really up to you what to do. I think I'm going to do this one, though, because I think it's just a lot easier to type into the calculator, especially because I already have the velocity in my y1. Okay, so again, don't forget that coefficient out front, 1/2 math 9 of y1 with respect to x. So I get about negative 79.147. Okay. Yeah? Yeah? Sure? No?
How accurate does the decimal have to be?
3 decimal places is always your...
Because I got 151.
When you did this?
No, I did the second way. Yeah.
Oh, the second way. Okay. Did you round intermediately? I'm guessing you rounded like this answer and then minus this answer rounded. Okay, so that would be it. So I would try not to round until the very end if you can. Hold off and round until the very end and leave it like that. Okay. Intermediate rounding is kind of like a no-no, I would say. So try not to round intermediately. Okay. Try to be as precise as you can in the meantime. I mean, I will say this, folks. If you're always concerned about precision, you can give as many decimal places as you want. The AP graders will not count off if you give 5 decimal places. They just won't look beyond the 3rd decimal place. They'll ignore the other 2 numbers. They'll kind of truncate it themselves, so to speak. So if you want, you can you can give as many decimal places as you want when you're doing your calculations, okay? So that way you guarantee accuracy and stuff, and then just, give your answer however many decimal places you'd like. Okay, of course, it's more writing and stuff, but that's the idea. All right, questions on any of that? Whew. All right, one more here, one more. All right, we're doing 3 today. I know that's a lot. We've only been doing 2 the last 2 days, but here we go. All right, so particle moves along a coordinate axis. Its position at time t in seconds is s of t equals, so the position function is defined as an integral here. Okay, where the graph of f is shown below as line segments and a semicircle. Okay, so most likely this would not be a calculator active kind of question. So let's try and do that without a calculator here. Okay, no calculator. All right. So letter A, what is the particle's position at time t equals 0? So that means we want to find s of 0, which would be equal to the integral from 3 to 0 of f of x dx here. Okay. So from 3, let's see if I can get this shaded in. Yeah. From 3 to 0. So we want to find the area of that region there. So what kind of shape is that? Trapezoid. You could also break it up into a rectangle and a triangle if you wanted to and put those together. What is the sign of this answer going to be? Negative. The region is above the x-axis, but we're integrating from 3 to 0. We're going backwards, and so our answer is going to be negative. So I'm going to go ahead and just throw a negative in front just to have that taken care of. I'll do 1/2. Okay, the height of this trapezoid is 3. Base 1 is 2. Base 2 is 3. Okay, you can stop there and circle that. Okay, or we can go ahead and simplify it too. So 2 plus 3 is 6. Half of that's going to be 3, so negative 9.
2 plus 3 is 6.
Mr. Wid. 2 plus 3 is 5, times 3 is 15. Negative 7.5. All right, so that's why we don't simplify arithmetic. Just circle your answer and be done, because sometimes we make errors. All right, letter B. What is the particle's position at time t equals 3? Okay, so yes, 0. So I just wanted to make sure we weren't given any sort of initial position, but we weren't given any sort of initial position. So yes, 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 yes. So yeah, I'm sorry, I was like checking to make sure I didn't miss a piece of information there. The integral from 3 to 3 of f of x dx, right, would give us 0. Okay, easy peasy. Okay, what is a particle's speed at t equals 4? Okay, speed is related to the what? It is the absolute value of velocity. So in other words, we want to find velocity at 4 and then take the absolute value of it. Okay, so, well, this is kind of a pain here. Okay, so how do we find the velocity if we're given the position? What do we do?
F is the velocity.
F is the velocity. So that's what I was trying to say. We take the derivative of the position, right? That's the key thing to relate here, right? So S prime of t, which is equal to v of t, right? That is the derivative of this integral. By the second fundamental theorem of calculus, it's just going to be f of t. So you're right. I just wanted to establish that it is. The v velocity is this function f that we've got right here. Okay? So, if we want to find v of 4, that's equal to f of 4. What is the value of the function at 4? -1, but then because we want speed, so it is 1, as you guys said. Okay, good. Questions on any of that? Okay, so letter D, approximately when is the acceleration of the particle positive? Justify your answer. Okay, so we want to know when is the acceleration positive. Okay. So if we're talking about acceleration, we're talking about the what of this function, the derivative of this, right? And so if the derivative of this is positive, how is it going to show up in the original function here? It's where the function's increasing. Exactly right. So for what intervals is this function increasing? 4 to 7, right? Okay. So from 4 to 7 we would expect. So let's see. I guess acceleration is positive for 4 less than t less than 7 because we'll say v of t equal to f of t is increasing on this interval. Bless you. Okay? So a little kind of like a backwards way that we normally describe things. Normally we're describing, the velocity is increasing because the acceleration is positive. Now we're kind of going backwards. We're saying because the acceleration, or because the velocity is increasing, therefore the acceleration will be positive on that interval. Okay? Kind of interesting there. Okay? Yep. Okay. At what time during the first 7 seconds does Fs have its smallest value? Justify your answer. So in other words, on this interval here. Right? Okay. So we want to find the smallest value, which in other words is the absolute minimum of S. Okay. So we consider the endpoints. What are the endpoints? Well, it's 0 and 7, so we want to find S of 0, which is the integral from 3 to 0 of f of x dx. We already have that. It is negative 7.5. Okay. We also want to find S of 7, right? That's the other endpoint, so that's the integral from 3 to 7 of f of x dx. Okay, from 3 to 7 of f of x dx, which is going to be, well, we have this region right here, which is a semicircle with a radius of 1. So it'll be negative pi times 1 squared. But they're going to add to it the area of this triangle right here too. So from 3 to 5, we have that negative area here. Negative pi times 1 squared, negative pi. We're going to add to it, bless you, this area, this rectangle here, 2 by 1, so 1/2 times 2 times 1. So we get 1 minus pi, or negative pi plus 1. Okay, that's S of 7. So there's our endpoints. We also need to evaluate our what, though? Critical points. You got it. So the critical points are where the derivative is 0 or undefined, right? The derivative of position is depicted right here, right? This is the derivative of position. Okay? So where are our critical points according to this? Oh, where's your question, sir? I did not multiply, you're right, I did not multiply by 1/2. Thank you. So it'll be 1/2 there. Thank you, yes, it is a semicircle. Should be 1/2. Thank you, Ursula, for saying that. Yes, 1/2. Oh. Mr. Wid. Negative pi over 2 plus 1. There we go. Okay. So there's that, there's that. Okay. I circled those, but well, we'll see if those are the actual answers or not. All right. So negative pi over 2 plus 1. Yes. Okay. So anyway, back to this, right? What are our critical points? 3 and 5. Okay. So S of 3 is the integral from 3 to 3 of f of x dx, which is going to be 0. Very nice. And then S of 5 is the integral from 3 to 5 of f of x dx, which now that Urja has corrected where my mistake was there, negative 1/2 pi times 1 squared. Okay, so negative pi over 2. Okay. So I should not have circled those there. Okay. So for what value of S does, or for what value, at what time, goodness, at what value of time? So at what time during those 7 seconds does S have its smallest value then? 0, right? At 0. 7.5 is the location of the absolute minimum value. I'm going to give the minimum value of negative 7.5 for S of t. Okay. We'll stop there, but I do want to talk about something. Caleb?
Do we really have to show, or can we just look at the graph?
Like figure it out from there? So, great question, right? You don't have to show all that work that we just did, but then my question to you is, how would you justify it? Your justification would then need to come in your kind of verbal, your like written description of how you then did it mentally. That's the catch. So it's kind of like a trade-off. You do this work, and then the justification is like, well, there's right there. There's the work, so there's the answer. Or you just say what the answer is, but then you got to be able to provide your justification in the words and stuff. So it's up to you how you want to do it. But yes, 2 different ways. One last thing I want to talk about here, okay, is that we very easily could have talked about net displacement here and total distance traveled in this problem. Okay, so let me just kind of go through that description of what net displacement will look like versus what total distance traveled will look like. Okay, if we wanted to find the net displacement, okay, of the particle, thank you, Cassie, from t equals 3 to t equals 7, for example. If we wanted to find the net displacement of the particle from t equals 3 to t equals 7, well, how do we find net displacement? We integrate what? What's that? Net displacement is just the straight up absolute, the velocity. It's the total distance traveled will be the absolute value. So for net displacement, this is like the more straightforward one. It's just the net change of the velocity. Net change of position, I should say. Net change of position, I mean. So from 3 to 7 of the velocity, like that. Okay, that yields this. Okay, and so you just do the integral as you see it there. Okay, just like do the integral from 3 to 7 of the velocity. Okay. The total distance traveled okay, of the particle from t equals 3 to t equals 7. That is the integral from 3 to 7 of the absolute value of the velocity of t dt. Okay? Now, when we had our calculators, this was easy, right? When we had our calculators, we could just plug this function in, evaluate from 3 to 7, integrate from 3 to 7, and be done. And here we could just plug this in with absolute value signs around it, integrate from 3 to 7, and be done. When we don't have our calculator, how do we account for the absolute value when we're evaluating this integral here from 3 to 7? How do we account for that? What do we do? Ignore the negative area here and just make it positive. Okay? So instead of making this a negative pi over 2 value, we would just count this as positive pi over 2, so kind of like the circle would be up here, and then adding on to it that triangle there. Okay? So that would be the difference here. For v of t, you're going to count this negative area and then add to it the positive area. That's your net displacement. For total distance traveled, you're going to make this area positive and then add on to it the area of the curve of the triangle. That's the difference. All right. We'll talk some more about that too, of course. Okay, but there it is. All right. That's all I've got for you guys today. Again, the homework is posted to the Google Classroom. Excuse me, the Google Classroom. But this was your homework from last night. On the back of that paper, that's your homework for tonight. Okay? This is the 2015 BC free response question. This is from the actual BC test, what, 2 years ago? 1 year ago, I guess? Okay, depending on... it was like, so 2016 was the most recent, well, 3 years ago, whatever you want to say there. 2 years ago, I guess. Anyway. Okay. Okay. Because we've had the 2017 test, we had the 2016 test, so this is like 3 tests back, I guess. 3 tests back is what I'll say, yes.
Are we in AB right now?
Yes.
Like, why is that BC?
So the BC test covers both AB and BC material simultaneously. And AB is just AB. Why? Because, all that stuff you learned in AB, you want to still be able to apply that too, so.
Instead of just calling it the ABC test, they just call it BC test.
They call it the BC test, right, but it covers both AB and BC. The idea being that if you pass the BC test, you get credit for both taking Calc 1 and Calc 2 as opposed to just like Calc 1. So, Ursha, yes, question? Yes, go ahead. Okay, so there's that. I know we had a bit of an intense day, so, you guys want to just, take a break, or if you want to get started on your homework there, that's fine. Problem set 4, like I said, is also up, and also there's the quiz review. I would suggest you start looking at that quiz review, too. We've, covered kind of the same thing over and over again, but it is not easy.